Welcome to the third and final video from chapter 18 in the book by Nate. This end of the chapter, we're going to introduce the ideal gas law, and really the focus is to concentrate on this right here, PV diagrams. PV diagrams is are the way in which we're going to describe a lot of processes involving gases for the next few chapters. They'll be really useful for us. Okay, so a lot of you have seen the ideal gas law in high school. So remember, this is an equation relating some of the state variables of our system. So pressure, volume, and temperature. This is an equation relating all of them. So the ingredients, so there are a few facts that go into this. And these facts were discovered over the years, a few hundred years ago by different people. And so one of these facts is that the pressure is inversely proportional to volume of a gas if the gas is at constant temperature. So I don't remember the name for all of these things. I'm pretty sure this one's called Boyle's law. One of the other ones is called Charles's law and Avogadro's law. So this is the statement that so suppose this sort of makes sense. If you have gas molecules and you increase the amount of volume, they're not taking as much space. There's not as much gas molecules pressing against the container. So this one sort of makes sense. Pressure is proportional to temperature at constant volume. So this also makes sense. If you heat something up, the molecules get more excited. They move faster. We'll see later. So it makes sense that they'll be pressing harder on their surroundings. The final one is that the volume depends on how much stuff you have, the number of moles. So given, holding everything else constant, the more stuff you have, the more volume. So you can consider the ideal gas law as just being a combination of these formula. So overall, we get pressure times volume is proportional to N, and I'm going to leave a blank here, N times T. Well, I can erase and rearrange however I want. So P times V is proportional to N times T. And we can simply make this an equality by introducing a constant. So we normally put the constant right in the middle there, nRT, PV equals nRT. So this, I suppose if there was one formula in all of the section on thermodynamics that you should learn, it's this one. We'll be using it a lot. Something you might not be so familiar with, well, I guess first I should label everything in here since it's so important. So this is pressure. This is the volume of our gas sample. This is number of moles of gas. So, by the way, this is number of moles of gas molecules. So remember from the last video that if you have a molecule of O2, so if you're talking about oxygen molecules, remember they come in pairs. Each molecule, each pair of O2 counts as one molecule. So this is the number of moles of molecules, not atoms. So if you have a monoatomic gas, it doesn't matter. Molecules and atoms, we can use those interchangeably. But for something like O2 or N2, you really have to talk about molecules there. T is temperature. T has to be absolute temperature, by the way. You cannot plug in, so because it's T there and not delta T, you have to use an absolute temperature scale. This is the thing that, this is, pressure can definitely never be negative, and so this quantity over here can definitely be negative. The temperature can't be negative. So you have to use that absolute temperature scale. So I'll talk about the SI units of all of these in just a second. And then R is a constant. So R in SI units is 8.31. Now, it turns out both of these sides are energy. Maybe I should start to use a different color for all these things. Things relevant to the units here. So all of these are energies. So P times V, if you plug in pascals times cubic meters, that's the SI unit for energy. That'll be joules. So as long as you're working in SI units, you're going to have a number of joules is equal to a number of joules. And in SI units, R is 8.31. It's a funky 3. 8.31 joules is what you're left with on the top. But remember, you're multiplying by moles and you're multiplying by Kelvin. So you'll have to divide out those units. Another common unit that you might remember from chemistry is 0.0821. That's if you have your volume in liters and your pressure in atmospheres, but you still have moles in Kelvin for your N and your T. So just as a small aside, this means, so if these two numbers are equal, that means a liter times an atmosphere is bigger than a joule, right? 8 joules is equal to a small number of liter atmospheres. That means that this unit must be bigger. So the conversion factor here is 1 liter atmosphere, which by the way is not SI units. 1 liter atmosphere is 101.325 joules. And this number should look familiar. Notice how it's a couple decimal places away from being the, I guess in this direction, it's a few decimal places away from being the number of pascals in 1 atmosphere. So the moving of the 3 decimal points is from liters and cubic meters, and then atmospheres and pascals, it gives the funky number. Okay, so this is the one that you should get used to using. I mean, this is the, well, I guess joules is the one that you should get used to using. So in chemistry, the liter atmospheres is more common. So just keep in mind, if you're plugging in pressure and volume in SI units, you have to use the 8.31 value. One other thing I want to mention about the ideal gas law. So N is number of moles and R is a number. So both of these, the number of moles that you'll commonly be working with is like 1 mole, 2 moles, a reasonable number of moles. You can rewrite, so nRT, PV equals nRT. I can multiply and divide by Avogadro's number. So I'm going to rewrite this a little funkily. So your book uses n sub a for Avogadro's number. This n sub a is the 6.02 times 10 to the 23. So I said I was going to multiply and divide by this number. So I'm not changing the equal sign here. I'm just multiplying and dividing. Now, Avogadro's number times the number of moles is the number of particles. This is simply number of particles. So this is capital N, number of molecules. So we have number of particles, and then R, which is a constant in terms of joules per mole Kelvin. If we divide by number per mole, then we get another constant that has different units. So I'll write down what this number is in SI units in just a second. And then we have T left over. So you'll also see the ideal gas law written this way. It means the same exact thing. It's just that N is a really, really big number, right? Number of molecules. Not moles of molecules, but number of molecules. So this is something like 10 to the 23. And then this number is really, really small. So see how they make up for each other. So a really big number times a really small number can be just like a number of order 1. This constant, we're not going to need it much in this chapter, but I want you to know it exists at this point. This is called Boltzmann's constant. And in SI units, KB is 1.38 times 10 to the minus 23 joules per Kelvin. Wait, that's not right. 8.31. That was 1.23. Pretty sure it's 1.23. No. 8.23, right? What the heck? There it is. 1.38. Wow. Shows you how long it's been since I've used that number. 1.23. 1.38. There it is. Right. 1.38 times 10 to the negative 23 joules per Kelvin. Notice how that doesn't have the mole. So that and the capital R are off by Avogadro's number. Okay, so this is a number you can just know that it exists right now. We're going to use it more in chapter 20 or so. K will be more common than R sometimes. Okay, so a lot of times problems involving the ideal gas law just say, pretend you're holding one thing constant, change another thing, what happens in response. So there's a lot of ratio style problems when you're doing ideal gas law problems. So this is one of them. What happens to the pressure if we increase temperature from 27 degrees C to 127 degrees C? So first of all, I want to point out that this could be considered a trick question because these temperatures are not in absolute temperatures. So the first thing you should do, if you're going to use the ideal gas law and you have degrees C, you have to convert to Kelvin. So to go to Kelvin from degree C, you add 273, 273.15 degrees, but your book doesn't even mention, I think in the previous section, they just say 273, so that would suffice. And notice how these numbers were chosen so that this simplifies nicely as long as it's in Kelvin, right? 300 Kelvin to 400 Kelvin. So let's answer this question. We have a rigid container. What happens to the pressure if we increase the temperature from 300 to 400 Kelvin? So the problem that we had before, problem from the start. So we have PV equals nRT. And let's look at each piece of this separately. So volume is constant. Well, first, since we want to know what happens to the pressure, let's solve for the pressure. Pressure is nRT over V. And really the thing that's changing is the temperature. So I'm going to factor out N, R, and V. These are all constants for this problem. But notice how it depends on the problem. You know that another problem could have the volume changing. So N times R over V are constant and temperature. So in this problem, if temperature is going to go up by a factor of 4/3. Remember, absolute temperature goes up by a factor of 4/3. So if the temperature goes up, because P is linearly proportional to T, that means P goes up by a factor of 4/3. So this is one way of writing the answer, or you could write P final is equal to 4/3 times P initial. There's a whole bunch of ways you could write it. That's probably the most succinct. Let's leave it like that. But notice how we had to, because of the number of straight variables that appear in the ideal gas law, a lot of times you have to know the process by which you're heating something up. So in this problem we had V is constant. That was a very important ingredient to knowing what happens to the pressure. You could also imagine that the pressure was constant. So you just have gas in a room, exposed to the atmosphere, and you heat it up. In that case, the pressure is constant because it's free to change its volume. So as you increase temperature, it's just going to take up more space, and it'll still be at atmospheric pressure. So a lot of the complicated things with thermodynamics involve just different processes, the different ways you could heat something up. So it's not just enough to know about temperature and heat. You also have to specify what's going on with other state variables that are going on in your system. And this is exactly why, so the book then goes into ideal gas law processes. Your book goes into more detail about what are some common processes. You'll notice if you scroll down a little bit, the book will sum up each process as a path on a PV diagram. So notice how there's pressure on the vertical axis, volume on the horizontal axis, no matter what they're talking about. And these graphs, you're going to hopefully love them by the end of the class, but maybe hate them in a week or so. So we want to say a little bit more about PV diagrams and what we're showing on here. That is gross. There we go. P and V. So the pressure is always going to be positive. The volume is always going to be positive. You're always going to work in the first quadrant here. So a path on a PV diagram. So first of all, just in order to draw any line right here, that's a line. It's not a straight line, it's a curve. So if you're going from some initial point to some final point, notice how I put a path right here. So that path could have been down and to the right. So sometimes we'll have arrows showing just to emphasize what's the initial and the final point, or it could be this way. But what's key to notice is that if you're defining a path, that means that notice how to draw a path, you have to know all the points along that path to draw it. And in order to define a point right here, that means the gas had to have a well-defined pressure and a well-defined volume at that point. So in other words, the gas is in equilibrium at every point along this thing. So a path, in order to draw a path, on a PV diagram, the process needs to be in equilibrium at every step along the way. And in order for that to happen, in order to have a well-defined pressure, you have to do this process very, very slowly. So it turns out, and your book says this, the critical question is how slow must a process be to qualify as quasi-static? This is the last paragraph right here on the left. That is a difficult question to answer. The textbook will always assume that it's quasi-static. It turns out to be reasonable for the types of examples and homework problems that we will look at. When we talk about engines and refrigerators in a couple chapters, that's the point. Like engines, have quickly moving parts, and you might think, well, this approximation is not a good one. It turns out it won't matter so much, because what we're going to do is we're going to be theoretical. We're going to draw paths on a PV diagram. Yes, maybe it's not ideal, but still, even with the theoretical case, we'll still see that there's a maximum efficiency for car engines. And we might get something like a maximum efficiency of only 20 or 30%. And we're being as theoretical as possible. So even if it's not ideal, even if it's worse than that, we've already said a lot just by saying that the maximum efficiency can only be, 20 or 30%. So this is, so in some sense, it's the fact that this is not, you might worry that it's not realistic, is okay for a few different reasons. So let me finish my sentence here. In order to draw a path on a PV diagram, the process must be reversible. And so you could think of this as happening slowly enough. So it's slowly enough that equilibrium is established at every point in between. So this is equilibrium at every step in between. At every step. Okay. So like this line right here, I've said what the pressure and the volume are at every moment in time. So your book defines a couple different terms. They call it quasi-static process. Your book is using quasi-static and reversible interchangeably. So quasi-static just means slow. Reversible means slow, and you can reverse it. But this book isn't really distinguishing between those two. So we'll be using the terms completely interchangeably. Quasi-static and reversible are the same thing. Okay, so that's one point about PV diagrams. Another point I want to make, so we'll talk about three in particular from this section, three particular processes. But before we even get into that, I want to mention one thing. So PV equals nRT. It's the one equation we've done today. If you solve for, so you're used to in math classes solving for the vertical axis as a function of the horizontal axis. So P is equal to nRT over V. If nRT is constant, so if you're holding temperature constant, there are a whole bunch of values of P and V that will satisfy this equation, right? So fix nRT, you could have maybe 1 times 1, or 2 times a half, or 3 times a third. The set of points at a fixed temperature is a hyperbola. So this hyperbola right here would be one single temperature. So this set of points right here is every one of these points is at the same temperature. This is called an isotherm. It's the contour in the PV plane that describes one temperature. So this is a particular temperature, T equals T naught. A higher temperature will have a higher value for the product of P times V. So if I freeze P, and this value of V corresponds to this temperature. If I increase V and hold P constant, this is a higher temperature. So if I start at a point on this isotherm and then I go in this direction, this is a higher temperature, higher temps. And these are, on this side, you have lower temperatures. Lower temperatures compared to any point on here. So notice how, if I start here and I go down, that's lower temperature. If I start at a point and move to the right, that's higher temperature. So you can go, if I start at a point and go up, that's higher temperature. If I start at a point and I go up and to the left, it matters how much is up and how much is left for higher temperature versus lower temperature. Or maybe I just wind up on the same isotherm eventually. So isotherms are a good way of keeping track of what temperature you're at. And we'll see next chapter that actually temperature is related to a lot of other things. So it's related closely to energy and it's related closely to the speed of the particles, actually the speed squared of the particles. Okay, so with that, armed with those pieces of information, we can look at the three types of processes that that have equations that nicely simplify, and also situations that arise in nature. And basically, it's the three processes are holding the various things constant. So we have three state variables that we're interested, P, V, and T. So the three processes arise from holding one of those three things constant and seeing what happens with the other two. So three processes. There's one more. If you've taken chemistry, you know that there are actually four that are common. We're going to hold off on adiabatic processes until the end of next chapter or chapter 20. It'll be a while before we get into that one because it involves heat capacities. We're going to have to say a lot more about heat capacity to study that one in detail. So three processes are, and I can just draw them all on a single PV diagram. So your book gives nice examples of physical situations where these would arise. So we've already seen one of them, and that's the constant volume process. And that arises if you have a sealed container. So I'm gonna draw the same initial point for all three of these things. This is going to be my initial point for all three processes. And I'm going to imagine heating up my sample of gas. So if I hold volume constant, I don't know what to do here with it. So this is some volume, V naught, P naught. So I'm going to hold volume constant. If I heat up a gas sample, I'm going in this direction. So I go from this initial point to this final point. So this process right here is called an isochoric process, C-H-O-R-I-C. One of the words constant volume process. So if I'm heating up a sample, the temperature is going to go up. And so notice how that's how I knew that the pressure would go up. That's how I knew that I'm going in this direction. Remember, I'm jumping onto a higher isotherm. So I can also just think about, drawing the dotted lines, there's one through here and there's one through here. So I jumped from the lower temperature to a higher temperature. So that's another way of visualizing this. Okay, that's the first process, and that's just sealing the container. If you're heating or cooling something, the pressure will change. Another thing is the constant pressure process. So I mentioned that you could do something in the atmosphere to have constant pressure. Another common thing, though, that your book is a fan of is a piston. So a piston will have its atmospheric pressure and then also the weight of, so see this mass M. So if you take mg and you divide it by the cross-sectional area here, that's an additional pressure that's on this gas. And that pressure is constant. So that this gas, if you heat it, it's going to take up a bigger volume. And the reason for that is if the pressure goes up, it's just going to push harder on this piston and the piston's free to move. So it's going to come into equilibrium until the forces on this thing cancel. So that requires the pressure on here be the same as before. So a constant volume process, constant pressure process will have P equals P naught, the initial pressure. And if we heat the gas sample, we're going in this direction. Okay, so we're jumping to a higher temperature, right? So this is called an isobaric process. So iso is same, and bar you can think of as, well, bar is another unit for pressure. So that's how I help remember it, or that's what helps me remember it. Same number of bars, same pressure. Isochoric, that's a weird word. I mean, that one's just a funny word. The other ones I just remember because they make more sense. Okay, so there's one more. So we've, in PV equals nRT, so I should keep this, this should always be in the back of your mind, right? In PV equals nRT, we've looked at P constant, we've looked at V constant. What about T constant? So for T constant, you might say, well, we've already looked at that, right? That's where the temperature is the same, so we're going to move along a hyperbola, and that's exactly right. So you might say, well, how do I know which way I'm going to go? Am I going to go this way or this way along the hyperbola? So for that question, we're really going to address it more so at the beginning of next chapter with the first law of thermodynamics. But basically, if you heat something at constant temperature, any energy that you give it in the form of heat, it's going to use to expand and do work on its surroundings. So you're giving energy in the form of heat, and the gas is wasting that energy, quote unquote, in order to push on its surroundings to get bigger. So you could try heating something. So notice if you heat something up at constant volume or constant pressure, the temperature goes up. But if you heat something at constant temperature, by definition, the temperature isn't going to change right here. So this path is an isothermal path, constant temperature process, isothermal process. So these are the three main ones, and your book gives an example of, if you have a water bath, you can force the gas to be at constant temperature throughout its process. So here it looks like we're decreasing the volume at constant temperature. And so I think so in this picture, it would actually be going the opposite direction, right? If you're decreasing volume, you have to go this way on the isotherm, right? If you're decreasing volume. So in this picture, you're decreasing the volume. It looks like the pressure has to go up, which makes sense from this picture, right? If you're squeezing this piston in, it would make sense that the pressure goes up. And this would have to be done obviously slowly in order for the gas to come to equilibrium along the way. Okay, so there's more information that we'll jump into in the next chapter.